Have you ever really thought about why a kicked ball makes that perfect arc through the air? Or what about that feeling when a car takes off and you're pushed back into your seat? Well, turns out those things aren't random at all. They're actually following a very strict set of rules. Yeah, seriously. You can think of it like a rule book for our physical reality. It's like the operating system that's running in the background, telling everything how to move, from a simple falling apple all the way up to the planets themselves as they orbit the sun. So today, we're going to open that rule book. The official name for this operating system is classical mechanics, and we are going to break down exactly how it all works. All right, first things first. What is it exactly? Well, at its heart, classical mechanics is the part of physics that's all about motion, the forces that cause that motion, and the energy tangled up in the whole process. It's pretty much the foundation that explains our entire everyday world. Okay, so before we can get into the why of how things move, we've got to learn the language to describe it first. Think of it as learning vocabulary. And that field is called kinematics. It's all about the what, the where, and the when. We'll get to the why in just a little bit. Let's kick things off with two words that sound a lot alike, but are actually super different: distance and displacement. Imagine this. You walk 10 meters forward, then you stop, turn around, and walk 5 meters back. The total distance you covered? That's easy. It's 15 meters. But your displacement, which is just the straight line from where you started to where you ended up, is only 5 meters. See the difference? Distance is the whole scenic route. Displacement is just as the crow flies. And that exact same logic applies to speed versus velocity. Speed is just what your speedometer tells you, how fast you're going. Simple. But velocity? Velocity is a bit more specific. It's how fast you're going and in what direction. So 50 kilometers per hour is a speed, but 50 kilometers per hour north, now that's a velocity. And the last piece of our motion language puzzle is acceleration. Basically, acceleration is any change in velocity. So yeah, when you hit the gas and speed up, that's acceleration. But here's the cool part. When you hit the brakes and slow down, that is also technically acceleration. And get this, even just turning a corner at a steady speed counts as acceleration because your direction is changing. Wild, right? Okay, so we've got the language down. We know how to describe motion. Now for the really fun part. Why does any of this happen? What's the thing that makes an object speed up or slow down or change direction in the first place? Well, the answer to that is the absolute star of the show. And that star is force. That's it. It's just a push or a pull. Anytime an object's motion changes, you can bet there's a force behind it. It is the why for every single acceleration we just defined. And this is where we get to the absolute heart of classical mechanics, the big aha moment. The thing that connects all these dots really came from one guy, Isaac Newton. He came up with 3 incredibly elegant yet powerful rules that explain pretty much everything about how forces and motion work. And here they are, Newton's 3 laws of motion. Number 1 is the law of inertia. Number 2 is that famous equation, force equals mass times acceleration. And number 3 is all about action and reaction. Let's break these down one by one. So the first law is all about inertia. The easiest way to think about it is that objects are kind of lazy. They just want to keep doing whatever they're already doing. If an object is sitting still, it wants to stay still. If it's moving, it wants to keep moving in a straight line at the same speed. You've felt this a million times. You're on a bus, it slams on the brakes, the bus stops, but you lurch forward because your body wants to keep moving. That's inertia, right there. So if things naturally resist changing their motion, what does it take to actually make them change? Well, that's where the second law comes in. It's the famous one, force equals mass times acceleration, or F equals ma. And what that really means in plain English is that the heavier something is, or the more you want to speed it up, the more force you're going to have to use. I mean, think about it. It's way easier to push a bicycle than it is to push a truck, right? That's the second law in action. Okay, so the second law is about how a force acts on a single object. But the third law, this one tells us something really deep. Forces never, ever act alone. They always come in pairs. The classic example is a rocket launch. The rocket blasts hot gas down, that's that action, and in response, the gas pushes the rocket up with an equal and opposite force. That's the reaction. You can't have one without the other. It's a two-way street. All right, so once you have Newton's laws in your toolkit, you can start to unlock some other really powerful ideas that are built right on top of them. We're talking about concepts like energy, work, and momentum. So, in physics, work has a very specific meaning. It's what happens when a force actually makes an object move. And energy is basically the ability to do that work. We usually break energy down into two flavors: kinetic energy, which is the energy something has because it's moving, and potential energy, which is stored up energy just waiting to be released. And this leads to one of the most fundamental rules in all of science: the law of conservation of energy. It says that you can't create or destroy energy, you can only change it from one form to another. The roller coaster is the perfect way to picture this. As it's being cranked up to the top of that first huge hill, it's building up all this stored potential energy. Then, as it crests the top and plummets down, all that potential energy transforms into kinetic energy, the energy of pure speed. All right, next up, we have momentum. The best shorthand for this is just mass in motion. It's literally an object's mass times its velocity. So something that's really heavy and moving really fast, like say a charging rhino, has an enormous amount of momentum. And surprise, surprise, just like energy, momentum is also conserved. So in any kind of collision, think of a game of pool when the cue ball smacks into the others. The total amount of momentum in the system before the crash is exactly the same as the total momentum after. The momentum isn't lost, it just gets passed around between the balls. So we've gone through the language of motion, Newton's master rules, and these big consequences like energy and momentum. But what's the big deal? Why does all this matter? Well, because these aren't just equations in a textbook. These are the literal blueprints for how our world is built. I mean, just look around. When you brake your car, you're using the force of friction. When you kick a football, you're dealing with force and momentum transfer. We already talked about roller coasters and energy conversion. Heck, even just walking is Newton's third law in action. You push the ground backward and the ground pushes you forward. It's absolutely everywhere you look. But it is super important to know where this rulebook has its limits. Classical mechanics is fantastic. It works almost perfectly for the world we can see and interact with. Cars, planets, bridges, you name it. But it does start to get a little weird at the extremes. When things get incredibly fast, like close to the speed of light, you need Einstein's relativity. And when things get incredibly small, down at the level of atoms, a whole different set of rules called quantum mechanics takes over. So when you boil it all down, classical mechanics is this beautiful, powerful operating system for our visible world. It lets us describe the dance of motion with just incredible precision. But it also leaves us with a pretty mind-bending question, doesn't it? If these are the rules for our world, the one we see every day, what are the rules that govern the rest of it all?